So this presentation will be divided into 5 parts, starting with the introduction. Then we'll go on to investigate different types of tunnel construction methodologies, and then we'll be talking about why finite element method is required for simulating these tunnel construction methodologies, and what will be the correct process of simulating these construction process. And towards the end, we'll be talking about what we learned from these sessions and what we'll carry home with us. So at the end of this session, all the attendees will be able to understand what are the different tunnel construction methodologies, what are the challenges posed by these construction methodologies, and why finite element method is needed for construction sequence simulation. And last but not the least, and probably the most important part of the presentation, is how to simulate tunnel construction sequence using finite element method. So first of all, let me begin by introducing the different types of tunnel construction methodologies that are available. So the selection of tunnel construction methodology is based on the geology. Are you dealing with soil type of strata or rock type of strata? It depends upon shape and size of the tunnel, whether it is a circular tunnel, it's a multi-arc tunnel, how big it is, and finally the depth of the tunnel. If it is very close to the surface, you can have open excavation. If it is very deep, you will have no option but to go with tunnel boring machines, and so on and so forth. So the most common type of tunnel excavation techniques that are available to the engineers are open-faced shield tunneling, tunnel boring machines including slurry shield and earth pressure balance tunneling, and sprayed concrete lining method, which is commonly used for NATM. I'm pretty sure the engineers in the session today are very much familiar with these common tunnel excavation techniques. So before talking about these excavation techniques in detail, let me quickly get your opinion about which construction methodology you find most challenging. So I'll open a poll now, and you can give in your votes. So again, the question is that what type of construction methodology that you find most challenging, not you do it most commonly. I can still see engineers are giving their polls. Alright, so thanks for your polling results. These results help us in understanding what are the main type of limitations or challenges that you come across different type of tunnel analysis. So the results are about 30 to 40% feel that open phase tunnel shield tunneling is most challenging for them. About 20% feel TBM is the most challenging tunnel excavation technique for them, and about 42, I would say, or let's say 40, feel that NATM is most challenging for them. So we'll keep these poll results in mind in framing our future upcoming sessions so that we can cater to your particular needs in a better manner. and I can still see there just 88% of the audience have voted, so there are a couple of more engineers who are supposed to give in their opinion, but I would say majority of them have given, so let's move on. So when we are talking about open phased shield tunneling, the things that we have to consider in mind is actually the shield itself. And the shield, most of the times engineers tend to design it for the worst case scenarios, whereas this shield is designed only for providing the temporary support for the time being. It is the permanent lining that we have to design for the majority of the loads or the worst case scenarios. And as you can see here, the surface is pretty open, and you can use different type of excavation tools to dig out the surface, and there is a conveyor belt that takes the debris out. And against this permanent lining, the existing shield can get the reaction to propel forward for doing the excavation. The face is usually unsupported, but it can be partially supported by different types of face jacks, plates, or even compressed air. Then we have tunnel boring machines. This is a closed phase system which advances through the ground by rotating heads. So this is the phase that actually does the drilling for you, and it moves forward by getting its reaction from the permanent lining that we have installed at the rear of this TBM machine. And to a larger extent, the shape of the excavation is limited to circular, because majority of the tunnel boring machines are in circular in shape. But now there are more advancements coming in that allow you to have different cross sections for the tunnel excavation using the same TBM machines. Then the sprayed concrete lining, which is called SCL and used for New Australian tunneling method. And as you can see, this type of tunneling methodology is very extensively used for soft soil scenario. And you can start the construction in multiple stages. You can start by providing a heading, then a bench, and then the invert. And whenever you are providing the support system for this type of excavation, you always intend to apply a temporary lining which is sprayed immediately after the excavation to stabilize the face, so that you can carry on the excavation of the invert. And then comes the permanent concrete lining. Now, engineers, to cut short the construction time, what they do is they have now started applying the permanent shotcrete lining with adequate amount of reinforcement right after the excavation, so that they can expedite the construction rate. And as you can see, the excavators could be different type of tools and machines for digging out the bench and the invert. The main advantage of NATM over other techniques is that the cross-section shape is no limitation. You can have different cross-section shape. It can be circular, it can be an ovoid, as you can see here. Now let's see the ground respond to this to different type of tunnel constructions. Whenever you are doing the excavation, you can say that there is a face that will always collapse towards the cutting head. Then there will be soil around it that will probably be relaxing and moving in the excavation. So what essentially is happening here is the excavation in the ground induces stress relief, and that causes soil movement towards the opening. and if there were no closure in the ground into the opening, then the volume of soil excavated will be directly equal to the volume of the tunnel that is created. But that's not the case, because the ground, however, does close into this opening. We have to take that effect into consideration. So this excess soil that we need, or the strata that we need to excavate, is often termed as the ground loss or the volume loss. And depending upon what kind of construction methodology you are using, these losses vary. So first of all, there is a face loss which occurs due to the excavation at the face right here, and it causes the settlement, and this is the usual profile that you can see when you are excavating at the face. Now if you are dealing with if you are constructing or excavating the tunnel based on NATM, then this profile would be different. If you are constructing it with TBM, then you will probably get this type of profile. So this face loss could be controlled depending upon what construction methodology you are applying. So if this face is generally supported, then this face loss could be minimized. Then we have shield loss that occurs due to the relaxation of soil around the shield itself. So the soil around it gets mobilized and it starts moving into the excavation. So it creates additional pressure on the shield itself, and this is termed as shield loss. Now again, depending upon what construction methodology you are using, what type of temporary support you are using, you may have a shield, you may not have a shield, then you have to take those kinds of soil movements into account. And then there is a post shield loss. This type of shield loss occurs in all types of tunnels, no matter if you have constructed it based on tunnel boring machine, or it's an open face shield, or if it is NATM. This occurs because of the void that is between the grouted and the shield itself, and these voids allow the movement of the soil later on, and that causes extra loading onto the shield itself, or on the lining itself. So the area or the length of the tunnel which is behind the shield experiences post shield losses. So from here you can probably get an idea that depending upon different construction methodology, the ground responses varies, and since the ground response varies, you have to take into account different challenges it poses. Alright, so now let's see why finite element methodology is used to simulate these tunnel construction, or why at all finite element analysis is needed in the first place. Well, this is the first question that every time we are talking to engineers who are looking at finite element methodologies for the first time, that they ask us, because there are so many non-numerical ways of obtaining good predictions of the likely ground response to the tunneling and the likely loads in the tunnel lining. So why do we need finite element methodologies? Because these conventional design tools are arguably cheaper and quicker to use. So to answer this question, I thought it would be better to include a slide on why not to use non-numerical modeling methods, and probably I believe this is going to help you also. So first of all, non-numerical methods are characteristically uncoupled. This means that the loads that are coming onto the tunnel lining are determined by one of the techniques, which is usually an elastic solution, and the movements in the soil strata are obtained by another method, which is usually empirical. So as you can see directly, these two techniques don't talk to each other. They are independent. loads obtained from your structural analysis, let's say, and the movements obtained from your empirical formula, there is a physical mismatch between them, and therefore these type of analysis or this type of methodology would not only lead to conservative design, but sometimes it might cause complications in your actual project during the construction. Then another major limitation with these non-numerical methods are that their empirical predictions are limited to greenfield solutions. This means that they completely ignore any kind of load pattern that could possibly affect the tunnel excavation. So they believe that there is nothing existing other than the tunnel itself. There is no superstructure or substructure in the vicinity to affect it, and they are not realistic because they don't consider the pore water pressure changes, the plasticity behavior of the soil, the lining deformation, the existing structures and their effects. So basically, due to these two main reasons, which are very integral to tunnel analysis, are not captured correctly by these non-numerical methods, and that is the reason why engineers started to look for a better solution, and they came up with numerical methods. So let's see why use numerical methods to analyze tunnel construction. So first, to simulate construction sequence, and this is all we will be talking about, is how to simulate the construction sequence today. To consider excavation forces like jack forces, face pressure that are occurring, and you will see as how two same scenarios could differ if they are not if the construction staging is not considered in between. Then dealing with complex ground conditions, to model realistic soil behavior, handle complex hydraulic conditions, deal with ground treatments such as compensating grouting, account for adjacent services and structures, simulate intermediate and long-term conditions, and deal with multiple tunnels in the close vicinity. And I believe if you see all these reasons, it will definitely establish a very strong case for you to use numerical models for your tunnel projects. And I believe, since I can see all the registrants, there are a good number of attendees who are already users of MIDAS GTS. So we have talked with most of the attendees here, and they are already on board with using numerical models for doing the tunnel construction analysis. So here I'll show you this case. This is a very simple example of a tunnel with connecting galleries. You see the results. It gives beautiful contours. The results are for displacements, and the results are 1.335, let's say. This is the same model, but the results are actually 1.82, and the maximum displacement is occurring at a different location as compared to the initial model. So what is the difference between the two? Why are the results different? The results are different because this one, the first example that I showed you, is not using any construction stage analysis. It's not considering the initial stresses. It's not considering the excavation process and how the soil deforms. It's not considering how the forces from the excavated soil strata is distributed onto the lining to support the overhead structure. So if that clearly goes to show that if you are using, if you have one problem, if you do with construction stage and without construction stage, you will be able to see the difference. And obviously, since construction sequence is more realistic, the results from construction stages will give you the confidence on your results. Now, before moving on, I'll first ask you, what are the major challenges you have faced when you are working on tunnel projects? So let me open the poll. And here you can select what are the main problems or challenges you come across when you're working on your tunnel projects. And this is a multiple choice poll, so you can enter or select multiple answers or your polls. So let me read out the options for challenges that we have commonly surveyed and put in here. The complex tunnel alignment is a problem or the challenge that they have to that the engineers have to face. Then there are sometimes shaft and tunnel connections are quite tricky. Then the effects of tunnel on the existing structures or vice versa, changing water level, and hitting poor or soft strata in between. So I can see 81% of the engineers have voted so far, and out of which 22% say the tunnel alignments have been complex, 31% say that the shaft connection has been tricky to deal with, and then the effect of, and 68% say effect of tunnels on existing structures has been the major problem. And 30% have found a problem in dealing with the changing water levels, and 68% people or the engineers here feel that or have faced challenges when they hit poor or soft ground strata. So again, these thank you for your polls, and these help us in framing our follow-up sessions so that it can be more directed more towards your practical needs. So now let me share with you what major challenges other engineers or like we have seen have experienced on different types of projects. Now this is a tunnel line. I'll not be able to disclose the projects here, but this is an ongoing or upcoming project where the line, if you can see, the tunnel alignment is not simple, straightforward. It has curves, it has reverse curves in between. So, and there are multiple underground stations on the lines that needs to be analyzed. Then not only these underground structures are to be analyzed, but also if you look at this particular junction, there will be tunnels crossing each other. It will be a big junction, so there will be the foundation of existing stations that have to be dealt with, and you have to see the effects of existing structures onto the tunnel alignment or effect of tunneling onto these existing structures. So these are some of the real challenges that can be met through finite element modeling. So like I said, underground structures on the project lines need to be analyzed, station foundations and connecting galleries that are together that give you a good reason to have a 3D finite element analysis done or to simulate these kinds of interactions. Then the complex tunnel intersections, as you can see here, are quite important to be tackled using a 3D finite element simulation. Then I've taken one example from shaft and tunnel connection. This is also a metro line, and you can see the connection of tunnel with the shaft. Now there were a couple of possibilities to be explored, whether the shaft or whether the tunnel should be monolithic with the shaft, or it can have an expansion joint there. And just by looking at the graphical images here, you can make out the tunnel stress distribution under the two scenarios and compare the results. So again, this is a problem that you cannot resolve with just simple 2D analysis or non-numerical methods. This requires 3D analysis with good construction methodologies. Then this is a very good example, again from a real project, of effects of existing structures on the tunnel, or the effects of tunnel on the existing structures. So this is a project where a pile foundation, as you can see, is being drilled to the existing tunnel lines, and engineers were supposed to evaluate whether the construction of these pile would cause severe effect on the tunnel, or will it be the post-construction effects, like the loads that will come onto the foundation. And here the engineers can see the two cases and simulate that, okay, post-construction loads will be greater than the loads or the deflection that it will be causing on the given tunnel. So you definitely need a 3D analysis here also, because you can then work out on different number of piles, different layouts, so that you can see what would minimize the effect on the tunnels. And you can at the same time see the stress distribution of this pile foundation on other structures in the vicinity. So it's not just always considered that, okay, there's a foundation and then the tunnel is going through it. It can be the other way around also. Then changing water levels. Now, tunnel construction takes a long time. It's not done in 1 month or 2 months or in one season. So if this is an example of a tunnel under a creek, and it's at significant depth, and depending upon the soil strata around it, there could be different type of drainage conditions and different pore water pressures. So with changing water levels, you have to take into account what would be the seepage condition. Would there be long-term effects on the tunnel? Short-term effects are the quick or the volume loss that you expect during the construction, but the consolidation is something that occurs over time. And if you're dealing with clay strata, then this problem is much more significant. So I'll take that up in a little more detail later on in the simulation part. Then this is an example from a nuclear power plant disposal site, and you can see this tunnel alignment is going pretty deep into the soil strata, and you can see that with these tunnel alignments at such greater depth, you have to analyze what different types of soil layers would you be intercepting, and this type of analysis could be done, and you can then find out that, okay, these are the regions where there is a risk of spalling, and they are the soft stratas. And in this soft stratas, since partially it is hard, partially it is soft, so you have to model the different soil layers with different constitutive material properties and slippage to, the interface surfaces to simulate the effects. And that is where a 3D FE model comes into picture. You can model the complex alignment of the tunnel, and you can investigate in more detail about that local soft rock spot or soft rock pocket. So I hope this has given you enough reasons to rely upon 3D finite element analysis for most of your tunnel jobs. Now I'll move on to showing you a simulation of this tunnel construction methodologies or tunnel construction process. But before this, you must be curious that why at all we need 3D analysis when most of the times we can do away with 2D analysis. And I will not argue that to any extent. There are places where 2D analysis is pretty handy and recommended, and there are times when 2D analysis have its limitations and engineers have to go towards 3D analysis. So as and when required, you have to make the decision of 2D over 3D. Now, engineers, based on our experience, are somewhat hesitant in performing 3D analysis, and we were very much interested in understanding what are the reasons that hold you back, or what are the difficulties that you face when you are dealing with 3D analysis. So I'll open the next poll here, and again it is a multiple choice poll, so you can give in your entries. So what are the difficulties that you experience when you're dealing with 3D modeling? Is it the limited knowledge about the benefits of 3D analysis? Or do you think modeling is tedious? Or you think result extraction and presentation takes a lot of time? Or you think you require extensive amount of training for learning the software that you would like to use? Or do you think the analysis that you run takes so much of time that you are discouraged for going for a 3D analysis? Almost 60% of the audience have given in their polls. All these polls are would be very useful for us to deliver our future lectures, so that we can cater to your or cater to your problems and help you in overcoming those limitations. So let me start sharing the results with you. So almost 82% of the audience have voted, and 15% of the audience feels that they have limited knowledge of the benefits of 3D analysis. They know 3D analysis there, they know how to do it, but they are not aware of what benefits can they get out of 3D analysis. Then almost 62% of the attendees today feel that the modeling is the most tedious part of 3D analysis. Then 35% say that their result extraction takes a lot of time, and 48% say that it requires extensive amount of training for learning these software. And then the 43% of attendees today feel that the analysis takes really long to run. So I would say the two main factors that came out of this poll is that modeling is tedious and extensive training is required. So once again, I thank you for your honest opinion about the analysis procedures, and we'll take them into account for our future sessions. So now let's move on to the simulation of construction process. So step 1 for simulating construction process is the geometry generation, where we have to basically define the alignment and the meshing to generate the model. The next step is defining the internal conditions, where you define the soil parameters, the structural properties for the shotcrete and the rock bolts. Then the external conditions, that is defining ground supports, seepage conditions, hydraulic boundaries. And then excavation simulation. Now based on what construction methodology you are using, you can choose relevant excavation simulations. And finally, the result extraction, that is what's the best way of extracting the results, what options are available in terms of contours, graphs, or animations. So let's start with the very first step, that is geometry generation. Now in geometry generation, the first step, as we all know, is reviewing the project sites, getting the recognized and survey data, getting the boring log data to come up with the basic inputs for generating the model. So the step 2 is generating the geometry itself. and in this process you have to based on the crude data that you have, you put into a software and generate these standard data. For this forms the basic geometry from which you have to start working. And once you have generated this geometry, in order to perform a finite element analysis, you have to make finite elements. For this, you do discretization. So essentially, discretization means generation of finite elements from the solid geometry to finite elements. So now I'll go over a demo where I'll try to show it to you as how complex the geometries could be and how they can be handled in the software to generate the models in no time. And the key of simulating these different types of complex boundary conditions or complex geometric conditions lies in how friendly or how user-friendly your tools are. So I'll quickly go into the software itself, which is MIDASoft for this demonstration, and I'll show you how to generate this 2-exit tunnel geometry. So this is how the software looks like. In the modeling part, if I go through, I have defined some material properties and attributes for the ground conditions, as you can see here, and I have brought in the basic geometry from a CAD source. So let me quickly show it to you. So these are the basic outlines that I would be working with, which is can be easily extracted from or brought in through the CAD sources. If you don't have CAD sources like DXF files, you can create these lines and everything easily from the graphic user interface also. So now let me start by creating a ground or the box here. So I'll just go to solid, click on the solid here, and given the length and the height and the width of the solid here, let me call it ground, and I'll use this preview to see the ground created here. I'll say OK here. So the ground is created. Now if you remember, there was an inclined surface with a complex topography. So for that, I'll create a surface from grids. So I'll give the size of the grid, the length in the x direction and the y direction, and for the elevation I'll quickly load from a previous from the field or the elevation data that comes from the field survey. So you can see these elevations at the grids are available. I'll click a preview button. So here you can see the surface created. I'll click OK, and then again hit the OK button. Now let me set the transparency of this solid for now. So I'll set it as wireframe so that you can see the surface that is created inside it. So this is the surface we just generated, and now I'll start creating the exits. So basically this solid above the surface is not needed, so I'll just trim the solid. So I just go to the option here to trim it. I'll select the solid that I want to trim. I'll select the surface using which I want to trim, and I'll give the reference point that I want to be taken out. I'll say the preview button. You can see the solid is trimmed and it maintains the topography here. So I'll click OK. So now this is the solid that I'm left with. Now I will quickly create the tunnel exits profile. So what I'll do is just go to extrude option, select the wireframe. So I'll select the profile here, select the direction. Now I want to go in this direction. I can just click on the axis here and enter the direction as 100 units, and I'll say preview. So you can see this entire line would be extruded. Say apply. Similarly, I'll bring in its transverse profile. So I'll click here, I'll say extrude here, and give the distance as 124 and say extrude. Then I'll say OK here. So you can see I've extruded these two from these wires to solids. And now obviously this is not how it looks like. I'm using these solids to generate the exact profile here. So I'll take out the common part. So just like we do in mathematics, we have Boolean operations. We'll apply the same operations here. So we'll go for a common part. We'll select shape 1 and shape 2 and then say preview. So the program will take out everything else, leaving the common part behind, and I'll say OK. Now once this is generated, I got the overall profile, and now I'll take out or add this solid to the other solid, that is the ground. Right now they are not connected to each other. So what I'll do is use an embed feature, select the solid, select the tool, and then say preview. So once I do this, you can see there is a dotted surface on the solid now along the topography. And once we have generated this, I can just hit the OK button here, and you can see the solid extra part has been taken out and it is embedded in the ground solid. Now I'll continue to create refining the profile. So I'll use this extrude feature once again and select this particular wire. That will give me the profile of the exit. The direction will be this axis, and the distance will be, let's say, 124 here, and I'll say extrude, so it will create the plane like this. I'll say OK here, and now using this particular surface that I've created, I'll divide the solid. So I'll go to divide by surface. I'll select the solid to be divided. So I'll select the solid that I want to divide, and I'll select the surface as shell here. So it'll select the surface, and I can also divide the neighboring solids. I'll hit the preview button, and you can see the program will divide this solid into number of parts, and then I'll say OK. So now you can see in the tree menu, different solid members are created. You can just check off to see which are what is the name to the given to the solid. You can control these names as well. So as you can see, this is the profile I have created, which is for tunnel excavation. So I don't need this extra or excess solid that is there, which is called extrude D3. So I'll just hit the delete button and hit OK to delete it. And now this is the tunnel exit profile. I'll start creating the tunnels. So for creating the tunnels, I'll just use the same extrude feature. I'll select the wireframe, and let me zoom in at this location so that you can see it more clearly. And everything I'm doing is just using my mouse button here. I'm not typing in any complex commands. And I can just select the wireframe for the tunnel opening, and then I can select the extrusion direction, and I can give the distance, and then I'll just say preview so that I can see the tunnels extruded there. I'll hit the OK button, and we're done with the tunnel generation. Now since this tunnel has also, just like the previous solid, needs to be connected, I don't need the extra part here, so I'll divide these tunnels with the given solids. So I'll use the divide option, select the solids to be divided. So I'll use 1, 2, and 3. So select the 3 solids that I want to divide, and the surface is shell. So I can just select the tunnel. The program automatically understands that this is a solid, but its outer surface will be shell, and it will create, it will make the selection. I'll just say the preview, and you can see the tunnels divided here, and I would say OK, like this. Now I want this tunnel to have opening, so I can delete the sections that I don't need here. So I don't need this one, I don't need this one, and everything. When I check off, I can see that they are hidden. I don't want this one, I don't want this one, so I'll just click here, I press down the control button and make multiple selections, and then just hit delete from the keyboard. In this manner, we have created the tunnel exits. Now I want this tunnel to be constructed in different stages, so I can divide them into different lengths. So for doing that, I'll quickly create a plane. So I'll just press down the wheel mouse button from the keyboard and rotate the structure here. I'll go to curve and create a rectangle. I'll just click here and let me do it again. I'll just click here and create an arbitrary rectangle, and since this rectangle will be used to divide the surfaces, I want this to be translated to different lengths. So I'll select it and then translate it. Let's say I want to make uniform copies of 10 units in against the direction of the axis, so minus, and let's say 5 times, and then I'll say preview, so you can see this is how it will be created, and then I could say OK. So these solids are these surfaces are created, and now I'll use these surfaces to divide the tunnel exits. So I'll just select, go to solid, select the divide here, and then select the solids to be divided. So I want to select the ground D2, D3, D4 and D5, and the tools. I'll go to surfaces and just press the shift button and select all the surfaces here, and then say OK, and the program will divide the solids. Now we are done with the entire model generation. Now what we are left with is defining the stages, the meshing size. So for this, I'll just go to the front view. This is the front view of the tunnel that we are working on. I'll just hide all the colors that I don't need, so this is all the geometry left here. And under meshing, we can specify the edge controls. So basically always it is recommended to control the mesh size as you go. So in areas where you want denser meshing, you can specify the lengths or the number of divisions you want, and you can go to the preview and see. This is the, if I go with number of divisions 4, if I give this as a length unit and then go to the preview, I can see it's a more uniform mesh. So in this manner you can control the meshing. And there is another way of controlling the mesh size. So let's say I want to apply it as a linear gradient. So I'll select the edge, let's say this one, and the reverse edge as this one. And in the starting, I want the divisions to be of length 10 units, and then towards the end it should go to 4. So this means if I hit the preview button, you can see the distance are higher here and that they are getting denser towards the end. And then I can say OK. So internally, the program knows along these edges what should be the mesh size that we should obey. And before applying the mesh, I can apply a control on the solid. So I can say that I'll have same soil property for everything, but these two are concrete blocks. So I'll select them and say no matter what happens, just apply the concrete properties to this mesh set. So right now they are all solids, and now I'll go to mesh and say auto mesh, and I'll auto mesh the solids with the size of 10, and I'll select all the solids that are there. So there are about 27. So I'll just press the shift button and select all and set the attribute as, let's say, hard rock. and then I'll say preview. So the program will show you the mesh size. So this means that wherever we have not defined the mesh size, the program will make divisions or the element length as 10, and it will interpolate from there. So I'll say OK, and the program will do the meshing. And while all other solids will have the property as hard rock, the concrete blocks that we selected will have the concrete properties even after meshing. So this saves a lot of back and forth that you have to do to adjust different meshes with different property types. And there you go. In about less than 19 seconds, I should say 18.367 seconds, the entire solid strata or the solid strata is meshed, and the model is good to go. Now you can see different mesh sets here. In mesh, you can see you can just turn off the main solid. You can see the excavation and or the tunnel exits with the tunnel mesh sets. You can give different names to these mesh sets as you go, but just for the demo purpose, I just stayed with the default options. So I hope this gives you an impression that if you have the right tools, you can do quick and easy modeling of any complex soil strata or tunnel layouts. I can see there are some hands raised, so please use the chat window to communicate with us. I'll be more than happy to take your questions either towards the end of the session if time permits. Otherwise, we'll definitely be contacting you through emails and helping you out with your questions. So we just saw the demo on geometry generation. Now let's move on to the second step of simulation, that is defining the internal conditions. And the internal conditions are governed primarily by constitutive material models. So basically what happens is that material properties and equilibrium conditions are used for stiffness relations, and structural stiffness matrix is developed using the element stiffness matrices. And the system of equations is then constructed for the whole structure. So cutting short the technical jargons, I will put it in a very simple manner. We all know this equation, F is equal to K times U. It's a fundamental relation. So when you are defining the constitutive material models, you are actually telling the program or the numerical solver that what values would be used for defining the value of K, which is the material properties and the element properties. So that's what you are entering in this step by defining the internal conditions. So when you are dealing with different types of analysis tools, you should pay attention to the different constitutive material models that are available to you. You have to use appropriate constitutive material models depending upon the soil strata you're dealing with. So you have to pick from Moore-Coulomb to modified Moore-Coulomb, or Drucker-Prager, or Duncan-Chang, Hook and Brown, jointed rock mass, modified camp clay, and sometimes you might even also need to use a user-defined material property for your for simulating the soil strata or rock strata you're dealing with. Additionally, you should not overlook the material models for your structural applications, like for the concrete and the steel that will be useful for defining your rock bolts and your shotcrete behavior. Then the third step in the simulation is the external condition. And in external condition, basically you are defining the boundary conditions, such as boundary displacement condition to represent the far field effect, then soil strata interfaces and the interface between tunnel linings. Then you define the hydraulic conditions at the far field boundaries. It could be steady state flow, it could be transient flow. So depending upon what soil strata or what profile you are dealing with, you have to define the water level. You have to consider that this is the fault line, so there should be interface between these layers. So again, making this technical relation very simple, when you are working or providing these boundary conditions and loads, basically you are defining the F of this relation. So you have given the K, you are defining the F, and what the program would internally do is use this matrix inversion method to find the displacements for you. Now, how these equations are set up and how these would interact with each other depends upon, it's a very big part of simulation. So when you are defining these external conditions, pay special attention to define the interface behavior, which will be useful for simulating the interface between lining and the rock, to simulate discontinuities. Even you are dealing with finite element methods, which is actually a continuous or a continuum model. You can still do analysis for rock strata with discontinuities, because what you can do is simulate different rock layers and apply a sliding interface between them that are controlled by the friction and other rock properties. And very important for determining the long-term effects are the seepage conditions. So you should have a tool that can consider the ground water flow for permeability functions and water content functions. And then the fourth part of the simulation is the excavation simulation itself. And this is the most important part of the entire simulation. So what I have done is I have divided this simulation into a number of topics that would be useful for your understanding. So first part is the initial state, then volume loss, then tunnel lining analysis, then changing water level, then construction schedule itself. So these are the 5 main topics that I will be touching upon and going over as what and how this could be, these simulations are to be done and accurately. So starting with initial state. So setting up of initial conditions is very crucial. What happens is, if we know what the history of the soil strata has been, then we should model it accurately. If we know what stress paths or stresses or prescribed displacement has already gone through the soil strata, then we should apply that onto the model in the very first stage. But most of the times, or for the practical application, what happens is that these details are not known to the engineers. We have very limited data at times. So if these are not known, then what we have to do is we have to input conditions that are appropriate to the greenfield site. So we have to apply by the means of constitutive material parameters, understanding what pore water pressure profiles are like, what are the K0 conditions. We have to simulate what would have happened in the past using these constitutive material models. And if there are any previous construction activities, so if you are creating the model, do keep those field conditions into your model. So if you have an excavation in a nearby location where you are considering the tunnel excavation, so in the initial condition, have that excavation or add another stage where that excavation has occurred. And for sometimes there are no previous excavations, so you can set the initial condition with all these basic parameters, let all the deformation occur, and then set that deformations to 0, so that you can focus on how much deformation or stresses would just your tunnel excavation activity cause onto the soil strata. So for this, when you are defining the construction stages, your first stage or the initial stage, you must set it to be to clear all the displacements. So what will happen, if you can see in this example, all the meshes are activated and ground conditions, the ground supports as boundaries are activated, and the load as self-weight is activated. Now what will happen? All the deformation due to the self-weight has already occurred in the soil strata, and we don't want to see the effects of those deformations onto your tunnel excavations. So what you do instead, you set all that as 0, treat the state as initial state, and thereafter whatever deformation has occurred is fine. Thereafter what will happen is something that is of your interest. But this stage is highly crucial to determine your initial, or determine your to starting your stress analysis. And sometimes you use K-naught conditions. Then this is the state that you should tie up for using the K-naught condition to begin with. Then the second most important thing is volume loss, and I know this has been a major topic of investigation by different research scholars over the time, and this is what is of major concern to the engineers also. And therefore there are several different approaches that explain how to consider the volume losses depending upon different conditions. So I'll cover all different types of theories that are out there and how they are simulated. So let's start with the gap method. In this method, what we do is, since we know that this is our final position of the tunnel and there will be definitely a volume loss or ground loss, so what we have to do is we have to dig our tunnel bigger than the actual diameter required, and this difference is called the gap parameter. So when we are beginning to do the modeling, we have to induce this kind of void in the mesh, let it deform by removing certain boundary traction boundaries, and then monitor the displacement of the nodes. And once the displacement of the nodes is controlled between the two stages, we realize that okay, now the soil strata has stabilized after this excavation, and that should be that should be equal to our required tunnel diameter. So it requires a lot of iterations. There are in plane and out of plane effects that we try to replicate, and this type of approach is applied for a 2D analysis, where there are limitations that you cannot apply a 3D analysis. So in 2D analysis you try to simulate the effect of 3D or out of plane effects using this analogy. And depending upon what construction methodology you are using, these the void size and the diameter or the initial position of the excavation would vary. If you are using TBM, then you can have more control over this opening size. But if it is some other construction method, then you cannot really control the size that much. So engineers go for a bigger diameter so that they can accommodate for the workmanship and account for the misalignment of the tunnel machines and all that. Then the next approach is the convergence confinement method. Now in this, we don't induce a void per se. What we do is, due to the excavation, there will be loss in the stresses, there will be unloading. So what we do is we activate the lining at the given location, and then we apply a factor called lambda here, and this value of this lambda goes from 0 to 1. So we start from 0, and at a prescribed value, let's say lambda d, we activate the lining. Now this prescribed value comes from engineer's discretion. Sometimes it's given in code, sometimes based on trial and error method to stabilize the excavation. So once we obtain or make an assumption of what lambda d value should be, we are able to activate the lining with the residual or with the remaining force. So the remainder of the stresses, the stress reduction, which is 1 minus lambda d times sigma naught, is then applied to the linings that are there. So this is another approach of simulating the ground loss or the volume loss. And then the third approach is progressive softening method. And this method is quite common for the engineers who are working on soil stratas with NATM construction methodology. And instead of applying the lining with that stress value, what we do here is we see that this is the method that we have to excavate. We reduce its modulus of elasticity by a factor beta. And again, this is based on the engineer's discretion and the field test that we can reduce it to. And in order to stabilize this mesh, we have to find out how much lining force that we need to apply to converge this this opening. So it is somewhat similar to convergence confinement, but it is just a different approach. So instead of working with the stresses, they work with the modulus of elasticity. The fourth and the most common approach is called volume loss method, where engineers don't work with modulus of elasticity, they don't work with stresses. They directly apply that this much should be the volume strain or the volume loss that will occur in the tunnel. And this is based on their predictive method, and this type of method can be applied only to soil strata where you can confidently and conservatively determine how much volume loss would occur for given tunnel size. Usually it is given in some percentage of the tunnel volume, and engineers refer to different types of codes and practices recommended by FHWA to determine that for this type of soil strata this much volume loss would occur, so we should start with a certain amount of value. But if you are working with finite element analysis, it is also worthwhile to perform a back analysis from this excavation to find out how much actual volume loss would have occurred. And depending upon the stiffness of the lining, even if let's say you have assumed 2% volume loss, so depending upon your lining stiffness, you should activate the lining stiffness assuming the volume loss would be lesser than what is predicted. So what will happen is that you should activate the lining increments as, let's say, 1.5% of the volume loss, because what will happen under the given loads, the lining will also deform and the volume loss would further occur. So if you activate the lining after 2% losses, then the lining will further deform and the losses would actually be greater than what you anticipate. So in order to get the final profile right, assume a little less than the actual volume loss depending upon your lining stiffness. So now the question arises as how to incorporate these different ways of transferring the stresses or assuming different percentages of stresses in the real modeling. So in order to simplify the construction analysis, if engineers like to work on 2D simulation, MIDAS GTS has a special feature for this purpose. So irrespective of what method you have applied to obtain the desired values or the starting values, you can use a feature called LDF, which is actually load distribution factor, in order to simulate this. So let's say you are doing a construction stage analysis in 2D and you want to see how the stresses are dissipated, or if you have taken out certain mesh sets, how the forces or the stresses are redistributed, because this type of force transfer is not instantaneous, that you excavate and all the load is directly taken up by your shotcrete or rock bolts. So depending upon how that force is dissipating, you can control these through different factors, and that is where this particular feature comes very handy. So This LDF is used to simulate convergence confinement or progressive softening in 2D numerical models. So let's talk about, if we are dealing with 3D numerical models, how to simulate it and what should we consider. So when you are dealing with 3D models, there are different types of force that you can easily compute or that are known to the engineers, such as the face pressure, such as the ground pressure, the jack force that will be applied by the tunnel machine onto the excavation. So all these forces, once they are computed, they can be applied in a 3D numerical model for simulation. So let's say this is the face pressure profile. So instead of this, if I can control my tunnel boring machine and angle and the face alignment, and let's say if I want to increase the efficiency, I want to have a different pressure distribution, I can control that. So here we are not assuming the out of plane behavior. Here we are controlling them by applying the accurate force value and simulating to see what and how it's going to affect our excavation sequence and thus the ground behavior. So here engineers can control these out of plane behavior better and don't have to singularly rely on empirical methods. So thus, use of 3D numerical model with construction sequence gives real ground response and confidence to the engineers on their results. I hope that answers some of your questions that engineers have been asking during the session. Now let's move on to another more, one of the most critical, I should say, the most important component of the tunnel excavation. It's the lining itself that determines as how the tunnel will perform and there will not be tunnel closures or failures. So simulating tunnel lining is possible through different types of elements. You can either do it using solid elements. So when you are using solid elements, the advantage is that it allows you to use a wide variety of constitutive material models. So you can play around with the structural property, the element properties based on the constitutive material models. It also gives you volume effect. So actually, when you are doing the meshing, it will show you that this is the volume of your taken up by your tunnel lining. But it does not give you structural forces, because from solid members you will always get stress values, and from stresses you have to compute the forces that is used by the design engineers for designing the tunnel linings. And then you have to maintain an acceptable aspect ratio for different element shapes. So this means that you have to maintain the ratio of length is to width when you do the meshing. So let's see what are the other alternates. So the other alternate is use shell elements, and the shell elements would remove the problem of any kind of aspect ratio control. It will allow you more. It allows more flexibility in mesh definition. But and one more thing, it is quite useful for extracting all the structural forces. But the problem is that shell elements don't have any volume effect when you're doing the meshing. Even if you use certain thickness of your shell elements and the program might show you in rendering that there is certain thickness to your lining, actually it is just a representative thickness that will affect its stiffness and will not simulate the volume effect. So engineers, if you are using shell elements, you will lose the volume effects and you will gain the structural nature. So keeping these points in mind, we at MIDAS, we have generated a special type of element called gauging elements. And the gauging elements is the feature that transforms the outer surface of your tunnel lining. So this is a solid tunnel lining, and its outer surface is transformed into gauging elements, which means that this surface will actually behave like shell members and give you the structural results that you need for designing your lining. So you are not adding a layer of another plate members and increasing the number of elements or duplicating elements. The program is allowing you to consider the outer surface of these solids as gauging elements that will behave like plate elements and give you the design forces. So as you can see, from these gauging elements you can extract the moment values, the force values, the shear values directly for designing. Thus, the advantage of using this gauging element is that you can capture the volume effect as well as the structural force effect from the same element. So this is how you model tunnel lining. But what about lining or the segments which are prefabricated and they have connections between them? So this problem is largely looked into by structural engineers, and what structural engineers do here is that they model it using shell elements, and at node A and B, if they are released for movement and they are not transferring any movement, there's just shear and axial force, they couple the behavior of these two nodes so that they can transfer just the axial force and shear but not moments. And if they are using the alternate of solid elements, then they do the same at the connection. So this method is quite okay for structural analysis point of view, but we are not able to capture the out of plane effects or interactions between this lining member with its adjacent lining member. And then you might ask that why are the out of plane stresses or interactions important? It is because of this. Due to different options of laying out these segments, whether they are unrolled, that means that all the tunnel expansion joints or the joints are aligned, or they are not aligned and they are rolled. So if they are rolled, then its behavior is different than if it is unrolled, and this clearly shows that you cannot obtain that behavior in just a 2D analysis of the lining through structural analysis. What you need here is a 3D model where you can have these shear transfers and moment transfers, or sorry, just the shear transfers and not the moment transfers, and the interface between one lining to the one lining segment to the other lining segment. And for this purpose, in MIDAS GTS, we have defined these new shell interface elements, which are primarily aimed at modeling the nonlinear behavior at the joints of these prefabricated liners. And if need be, you can also define your own type of shell interface. And this is particularly relevant for tunnel boring machine analysis, because in tunnel boring machines we usually install the prefabricated liners, and we can play with their orientations to achieve the desired effects. For that type of construction process, these interface members are especially useful. And then you can see the results and the behavior. So you can see how these tunnel lining members are actually interacting with the adjacent members. And you can see if the maximum of the tunnel lining member occurs at one location in one lining, it may not be exactly the same for the adjacent lining. So depending upon the interface, the force transfers vary. And here we have simulated the rolled condition, so therefore the forces and the stresses are varying as you go along the length of the lining, and this gives you much more confidence on the analysis that you have performed and on the results, and you can actually optimize your design results and save on your material cost. Then the next in line is the changing water level, and I realize it is not one of the main concerns of the attendees here today, because out of the entire audience, just 23% said that this is one of the challenges that they have faced. This is the changing water level is of a concern if you are dealing with clay soil strata. So if the excavation is taking place in low permeability clay soil, then rapid construction process may result in no volume change at all. And that is, we are doing excavation in undrained ground condition. But in clay soil, what happens is after the tunnel has been constructed and the lining is installed, the ground displacements are likely to be seen to continue at the surface. So you'll see the surface still deforming even after you have finished the construction and you have installed the linings and all. So these are the long-term effects that happen. And this is happening due to the consolidation movement and the dissipation of pore water pressure from the clay layer. And this deformation will continue to occur until unless the pore water pressure equilibrates and appreciates the presence of the tunnel interface there. So till the time it stabilizes, you will continue to get deformations and thus additional forces on the tunnel. And recently there have been a couple of cases where the tunnels have collapsed under these kinds of or have shown increased deformations that have rendered them unsafe for using till further repair because of these effects. So long-term effects are equally important if you are dealing with soil strata that have clay or unconsolidated layers. And for this purpose, while simulating this in your numerical analysis tool, you should alternate the seepage analysis with your construction analysis. So once you see the seepage, then you do the construction, and then you have to alternate the effects. And you must consider the transient seepage analysis as well, where you can vary the seepage flow with time. Now the final part of construction simulation is the construction schedule itself. And what happens is that this is how your construction schedule looks like in your spreadsheets. So you have certain nomenclatures that you have to start with. You have to apply certain type of shield or certain type of grouting at certain time step, and then there will be tunnel boring machine or the tunnel excavator moving in the forward direction. So if you really break it down, you will be able to put it down under 3 headings: what methods you need to deactivate and when, and what methods you have to activate and when. Similarly, the second tab would be the loads: what type of load you have to activate in which stage, and what load you have to deactivate once it is no longer there, or it is associated with your construction equipment and it is moved on from that location to the other. And then finally the boundary conditions, because your soil will be deforming, so you will have your lining members placed, and if there is additional support or internal support that is applied to hold the linings in position or giving some time for curing, so for during that time if you have temporary boundaries, then that can be also activated and deactivated. So it seems complicated, but once you break it down into the construction schedule, you can easily apply it in the construction staging. So how to do this? Let me quickly show it to you in the program itself. So this is a tunnel example here, which is being constructed using tunnel boring machine, and I'll quickly show it to you as how the construction stages are set up. So if we go to model and construction stage, we define it using a wizard, where I can see all the initial conditions. Let's say ground, inner circle. These are the initial members that should be activated. So that goes in the IS, that is initial state. Ground support has to be activated, so I'll drag it and drop it here. So you can see a dash here. And then for loads, it will be self-weight that is added only. So this defines my first or the initial construction stage. And thereafter, I can just open a construction schedule, something like this. Just selecting what mesh sets should be activated and when it should be deactivated. Similarly for loads, and just copy and paste it here. Hit the assignment rules, and this is how the program defines it. You can then hit the OK button, and now you can look at the construction schedule. So if you go to construction stage, define construction stage here. You can set the first stage to be clear of displacements like I defined earlier, and just hit save here. And then if I check on this activate button, I can cycle through the construction sequence. So if I go to the second stage, you can see the excavation has occurred, and this is just the outer shield, and so on and so forth. So you can see the excavation is occurring in different stages, in different steps, as the tunnel boring machine is moving forward. And after a certain stage, we start installing the segments. So if you see the previous stage, there was just the tunnel shield, and when it is moved forward, then we started installing the segments, which could be precast, and then so on and so forth. So this type of construction can be proceeded. So it's a very simple simulation. All you need to know is just number the mesh sets accordingly, and then fit them into the construction schedule, and just apply it onto the model. So then the last part is result extraction, and this is a pretty big challenge, because there are several tools out there that take you to a point where you can create a model, run the analysis, and when you have to extract the results, it takes another several hours for interpreting the results. So the tool that you are using with should be able to extract the results for 2D members, for 3D members, for the ground strata, and you can also should be able to generate these kinds of graphs, which is usually the displacement of the crown as the construction activates. So you can easily capture how much deformation is occurring, and that can be related to your volume loss. You can generate the settlement profiles in spreadsheets, and directly it can be read to generate the graphs. And another good way of representing your construction and giving a presentation to your clients is through animations. And you can create the animations and save them as an AVI file for your own display. And then there's some tools also offer you walkthrough or fly-through options, where you can walk through your tunnel linings or the tunnel paths, and wherever you see high stress concentration, you can just click there, and the program can show you the stress values at that location. So there are all different result extraction procedures available. Now I would like to draw your attention towards a comparison of 2D analysis with a section in 3D, and this comes from a real project which has been recently published in the Tunneling Journal, and here as you can see, it is quite difficult. If you have to do a 2D analysis, you would have to analyze this cross-section at different locations. So this section is different from this section, and then there is a section and they are not perpendicular, so they are at an angle. So you have to analyze all different cross sections if you are dealing with just a 2D scenario. And so what the engineer in charge of this project did is he compared the results with a 2D platform with a section in 3D platform, which is MIDAS GTS, and you can see the results for the overall ground displacements are same, because this is how the ground responses. But if you see, the forces that are coming into the members from 3D analysis are lower than the 2D analysis, and this goes to show that the out of plane effects. So the out of plane forces are taken up by the neighboring members, and you can see the unfactored axial lining loads have been reduced, and the unfactored maximum bending moment has been reduced. So 98% of the points have much lower bending moment as compared to the maximum value which is obtained from a 2D analysis. So in this manner, engineers can optimize the design, and this results in huge savings. So this brings us to the final part of the presentation, where I will be concluding of the things that we have learned so far. So first of all, numerical analysis are useful in mitigating real field challenges like complex tunnel alignment, tunnel connections, existing structures, and changing water levels. The results with and without construction stage are simulated are different, since the soil strata response keeps changing with excavation. Initial state is most important to normalize the previous history and consider the effect due to tunnel excavation only. Ground response to tunnel construction can be accurately assessed by 3D numerical model with construction simulation. Spatial elements like gauging elements and interface elements produce efficient result without losing the accuracy for tunnel lining. Depending upon drainage condition, consider changes in water levels very closely, and 3D simulation leads to optimal design. And last but not the least, a user-friendly interface enables engineers to enjoy the benefits of 3D numerical modeling through easy model generation and efficient result extraction. And just to further our points, we do provide these seminars and sessions for free of charges, so you can come in, you can learn about different advancements in the industry of geotechnical engineering. If you have questions regarding numerical modeling and numerical analysis, you can join our MEC courses that are currently going on, and you can keep learning about not just the software aspect of application of numerical modeling, but also the theory behind it. So here we are ready to support you on both grounds, software usage as well as theoretical background.